Hi. So in the last few videos, we talked about linear regression, a supervised learning algorithm used to predict continuous variables. So in this video, we'll be talking about the implementation using Python. So we'll be demonstrating the linear regression implementation with two approaches: the analytical solution, also called the closed form solution, and the gradient descent optimization. The tutorial will start off with some synthetic data generation. We'll be using NumPy to generate random data with controlled slope, intercept, and noise. Then we'll move on to an interactive visualization using IPy widgets to allow a dynamic visualization of the linear regression line. We'll be changing the slope and the intercept to see how the line changes and see its relationship with the data as well. Then we'll move on to the analytical solution. We derived a few equations for the slope and intercept in the previous videos, and now we'll try to implement them in Python using NumPy and create a class of linear regression that uses these analytical solutions to come to a conclusion and fit the line on the data. Next, we'll be implementing gradient descent. We talked about in the last videos how we don't really use the analytical solution due to different constraints, and the gradient descent iterative approach using a learning rate and multiple iterations is the way to go. We'll be implementing a different class using this approach. Finally, we'll see the results and we'll compare both of them and see what result is better than the other, and we'll come to a conclusion to this particular problem. So stay tuned for, and next up is the tutorial itself. So here we are in Google Colab. It's an environment where we can write Python code on directly on our browser. It's hassle-free. It's pretty easy to use. I love it. So we start off by importing the regular modules such as NumPy, Matplotlib, IPyWidgets, IPython display. All of these will be used in the tutorial, and I'll show you where and how. So let's run the first cell. The second cell has two particular functions. One is generate data and the other is to plot regression. Let's talk about generate data first. What it does is it takes a random number generator from NumPy and creates a scatter plot using the particular parameters that we pass into the data. In our case, you can see that the slope is 2 and the intercept is 5, and it also adds some noise to the data so that it's not completely linear and it has some variation. And then it generates that data and returns it into a tuple of x and y, x being our data samples and y being our result. Then there is the plot regression function, and all this does is plots the data itself as a scatter plot in blue and then creates a line in red. And we plot that and use the IPyWidgets module to create a interactive sliders to see how changes in the slope and the intercept change the line itself. So let's run this function and see how it actually works out. So we can see that the dots in blue are the actual data and the line in red is the ideal line that we created in the first place. And above here we have two sliders, one for the slope and one for the intercept. So let's change the slope first and see how it changes the line itself. So let's increase it. And we can see that the trend has a higher slope. So with each change in x, there's a greater increase in y. Let's try to decrease this. Let's take it into the negatives, and we can see now we have like a negative trend instead. Let's take this back to 2, and from there, let's move on to the intercept. So it's at 5 now. If we reduce this, we can see that the line itself just shifts down to -5, and if we try to increase it, we can see that the line's intercept has shifted to 9.1 instead. And this is essentially the knobs that the machine learning model tries to tweak when we're trying to fit our model with the data that we have itself. So let's now move on to the class using analytical solution. So here it is. It's already implemented. And I'll go through the code itself, and you guys can reproduce this to see how it actually works and play around with it. So it has four particular functions. The class itself has an init function, which initializes whenever you create an instance of the class. Uh, in our case, the only two things that we need are the slope and intercept here. Then there's the fit function where we pass in the data x and y, and we use the analytical solution derivatives that we found out to calculate the slope and intercept. The equations that we calculated before are just written in a Python fashion in Python using NumPy. Finally, we do a prediction, and prediction we just pass on the x, which is the data, and we put that into the model itself, which is just a linear model, self.slope multiplied by x plus the intercept, y is equal to m is equal to c, and then we calculate the mean squared error um, of the prediction, and we return that. And when we run this particular class, we can see that our fitted model has the equation of 1.71x plus 5.32 as the intercept, and the mean squared error is 2.63. So that is essentially the closed form solution or the analytical solution. Now you might be wondering why this isn't exactly 2 and 5. Well, you might remember up here that we didn't exactly make a line with slope 2 and 5. We actually added some noise in it as well, which is causing this slight change in the slope and intercept. So that's the solution analytically to our particular problem. Now let's move on to linear regression using the gradient descent method. And over here we have the same four functions: init, fit, predict, and mean squared error. The only difference is in the first two functions, the init function and the fit function. So in the init function, we have two particular parameters that we can pass on: the learning rate and the iterations. As we talked about it before, the learning rate is essentially how big of a step we want to take after each iteration to see how our model is performing and to re-evaluate. And the iterations are just the number of steps that we want to take in gradient descent optimization. Next, in the fit function, rather than using the analytical closed form solution, what we do is that for the number of iterations, we make some predictions. Using those predictions, we find the derivative of the slope and the derivative of the intercept. Both of these equations we have derived in the previous videos. And then we try to update the slope using the learning rate and the derivative, and the intercept using the learning rate and the derivative of the intercept as well. Finally, after each iteration, we're calculating the mean squared error, and we are printing that value as well to see how the error reduces with each iteration. The predict and mean squared error function are the same as before. And then we just create an instance of the model called LR. We fit it on our data. And let's see if that for 500 iterations with a learning rate of 0.01, what our result would be. And here we are. Let's start off at the beginning. It's 500 iterations, so it's quite far up. We just scroll up and we can see that our iteration 1 started at the y is equal to 1.7, which is about what we had in the analytical solution, but the intercept is pretty low. It's close to 0, and our mean squared error is more than twice of what was in the analytical solution. But with each iteration, we can see that the mean squared error is decreasing until eventually, after 500 iterations, we can see that our model has almost converged to the point where the analytical solution was 1.769 plus 4.925. And the final mean squared error is 20.66, which is pretty close to the 20.63 that we had in the analytical solution. So that's basically it about the linear regression model. I hope that this tutorial gave you a bit of an understanding. Once again, to recap, we imported our functions, we generated some random data, we plotted that data on an interactive graph. After that, we created a linear regression class where we used the analytical solution to find the best fit of our model. And then we used the gradient descent optimization instead in another linear regression class, and saw how that both of the solutions essentially come up to the same answer. I hope this video was informative and gave you a better understanding on how to implement linear regression in Python using NumPy. Thank you. If you enjoyed this video and learned something from it, I hope you could share it and like it so that more people can come across it and learn about this particular function as well.